Does anybody want to guess what the term linearization means? What about a line?
Taking a curve into a straight line.
Yeah, it's actually pretty much exactly right. We're going to take a curve and we're going to make it into a straight line. Now, how can we take a curve and make it into a straight line? Why? What did you say?
Change the axes.
What do you mean by that?
Like the independent axis, put like if it's y equals x squared, you can put x squared on the x-axis.
Oh,
that's basic.
no.
Is that something?
Change the
No.
windows.
What?
Change the window.
We could do that. Okay, what do you mean by that?
Like make it really small, little box.
Yeah, zoom in, right? So if you take a curve and you zoom in on it, if you zoom in enough, it's going to look like a line, right? Some curves you don't have to zoom in very far, particularly, well, especially when we're looking at certain regions on a curve. You don't have to zoom in very far and it'll look like a line. Some curves you have to zoom in a lot to make it look like a line. And I want to look at an example today that's in the book of one of those, that you have to zoom in a lot before it looks like a line. It's something that we want to do or understand how to do, because if we can make a curve look like a line is a lot easier to work with than a curve. So if we want to approximate values on a curve, we can use a line to do that. So this idea of linearization is we're going to use a line to approximate a value on a curve. And we'll look at some examples here that are pretty... they're pretty straightforward examples, and they're pretty. I think they're good. They display linearization really well. I didn't say that very well. Sorry. They're pretty practical, or at least they can be. So anyway, the idea here is we're going to zoom in on a line enough that it looks, or zoom in on a curve enough that it looks like a line. And basically what we're going to do is we're going to approximate a curve with a line. So this is a formula that we're going to use. What do you think L stands for?
Linearization.
Yeah, the linearization. So the linearization of a function is equal to the function at some point plus the derivative of the function at that point times the difference between the x value and that point. And let me just draw a picture of what's going on here. So let's say we have a function that's a curve, and we want to approximate this function in some region. Now, one thing we need to understand is if I want to know what the value of this function is at some point, let's say I want to know what the value of the function is right here at maybe, let's say this is 2 on the x-axis, so maybe at like 2.1 something. Rather than plugging 2.1 into some big complicated function, I might be able to use a line to approximate it close to 2. I wouldn't want to use a point out here at like 6 to approximate the value of the function at 2.1. Why not? Why would I want to use a point here at 2 rather than a point at 6 to approximate the value of the function at that point? That's closer, right? That's an easy question, I think. So what we're going to do is we're going to use the idea of the tangent line. And let me draw a tangent line here for you. We're going to draw a tangent line at 2. And if you notice, the value of the function at 2 is very close to the value of the line at 2. In fact, because of the width of the lines and the curve, they still overlap here. So at values close to 2, this tangent line here is going to have values really close to the function. So within a small region, that line and that curve are going to be essentially the same thing. Does that make sense? Now we are going to have some error. We'll talk a little bit tomorrow about how we calculate the error. Basically, to actually calculate the error, we figure out what the value is on the line, figure out what the value is on the function, and we subtract it. But we can make a reasonable guess at the value of the function and have an idea of what the error is going to be without actually having to figure out the value of the function. And that is a practical thing too when we're talking about models in the real world. If we're going to model something, we want to know how far off we might be. So where does this come from? Let's talk about this real quick. Instead of a 2 here, let's put an A. And let me just get rid of this point here. I don't need that anymore. So what's going on in this equation? What's that? Okay, so we're plugging A into f of x, and what we get then is the point here at a comma f of a, right? Okay, so where does this equation come from then? What is that? Let me say this. The L here, the linearization, is just the equation of this line. So this is like y equals something when we're talking about the equation of this line. So if I change this to y equals, well, it's close to mx plus b, but we have that f of a there. The f of a is the value of y at the point, right? So the value of y at the point we might call y1 here. This is the value of, a is the value of x at that point, so that might be x1. So this would be f prime of x1 times x minus x1. Does that look familiar? It's really close to something. What does the derivative tell us about a line? It tells us the slope. So if I replace that with m, it's getting really close to what? The point slope formula. So this is really just the equation of the tangent line. So it's some big fancy formula, but it's the equation of the tangent line. So what the linearization formula says is close to a point, close to the tangent point, or the point of tangency, the function and the line are pretty close to the same thing. And that's all it's really saying. Okay? So let's use it. Let's do something useful with it. So we want to approximate the value of the square root of 50 without a calculator. How does that have anything to do with what we just talked about? Okay, we had a function, right? What kind of function do you think we might use to do a problem like this? Okay, I like that. So let's just say, to start with, that f of x is equal to the square root of x. And we don't really need it, but I'll draw a picture of the function. I think we have a pretty good idea of what the square root function looks like. So that's going to look like this, right? And I'm going to scale it so that we get the points that we need here. So let's go all the way out to, what do you say? What should we put there? 15? No, I'm sorry, not 15. On the x-axis, well, we need to get 150 somewhere on there, but I want to go beyond that. 200? Okay. 200 is good, except I don't know what the square root of 200 is, so I don't know what the value of the point is going to be there. Maybe 225. What do you think about that? Do you guys see why I want to use 225? Because I know what the square root of 225 is. So the point here at 225 is going to be what? 225 comma 15. Okay. And we want to know what the value of this function is at 150, which is going to be, I don't know, somewhere in here. Doesn't really matter exactly where it is. So we want to know what the value of the function is at 150. What could I do? Okay, so we know the square root of 144 is 12. That's a really good start. So 144 is going to be really close to that, and we know the value of that is going to be 12. Which means the square root of 50 is going to be a little bit bigger than 12, right? Well, let's be a little bit more accurate, though. We don't want to be just a little bit bigger, but we want to know how much bigger. So what do we want to do? What is the linearization going to look like? I don't really care what it is right now. What's it going to look like?
A line.
Okay, there's going to be a line. Is it that line? No.
Tangent line.
Okay, the tangent line. Is it going to be the tangent line here? Or here? Or here? Or here? Where? Not at 150. Here's the thing. We want to approximate the value at 150, but we don't know what the value at 150 is. So if we don't know what the value of the function is at 150, then we can't really write the equation of the tangent line, right? So if we want to write the equation of the tangent line, we need to know what the y value is also. So where do I know what the y value is?
44.
At 144, right? So I'm going to, I want to look at the tangent line through the point 144.12. Let me move that just a little bit here. Oops. Now, I wish I could zoom in here for you guys, but you can kind of see that this point here that we're looking for the value of, the y value of, is essentially on that tangent line, isn't it? So what we're going to do to approximate the square root of 150 is we're going to figure out what the value of the line is at 150 rather than the value of the square root function. Does that make sense? Okay, now we had that formula. We could use the formula, or you could just use the tangent line. Let's go ahead and use the formula for this example, and then for the next example we'll use the tangent line. So the linearization L of x is going to equal what? What are we going to put in for a? 144. So it's going to be f of 144, which is 12, plus the derivative of the function at 144. And does anybody know what the derivative of the function at 144 is? What are we probably going to have to do? Take the derivative, yeah. So the derivative of the square root function, remember that is x to the 1/2. So the derivative is going to be 1/2 times x to the negative 1/2, which would be 1 over 2 square root of x. You guys okay with that? Do I need to explain that in a little more depth? There you go, okay with that. Okay. I'm going to kind of assume from here on out that you know how to take the derivatives at least. So what is the derivative then at 144 going to be?
124.
Yeah, it's going to be 1 over 2 times the square root of 144, or 1 over 24, times x minus 144. Now, this actually will give us the value of any point on the green tangent line here, but I want to know specifically what the value is at 150. So what do I do to do that?
Plug in 150 for x.
Thank you. Plug in 150 for x. So the linearization at 150, which is going to give us approximately what the square root of 150 is going to be 12 plus 1 over 24 times 150 minus 144. 150 minus 144 is 6. 6 over 24 is a fourth, right? So it would be 0.25. So it's going to be approximately equal to, the linearization is going to be equal to 12.25, which means then that the square root of 150 is approximately equal to 12.25. What do you think about that?
Pretty easy.
Pretty easy? Okay, so then the second part here says use your calculator to check the accuracy of your answer. I see at least one person doing that already. What's your calculator say?
12.2474.
How do we do? It's pretty close, isn't it? So rather than saying the square root of 150 is just a little bit bigger than 12, we can say pretty close to exactly how much bigger than 12. It's accurate to 2 decimal places. If you round to 2 decimal places, it's 12.25. So that gives us a pretty accurate answer without having to use the calculator. Now, like I said, the calculator would give you the answer fairly accurately, fairly quickly, very accurately, fairly quickly. But you can see why this would be useful before calculators were readily available, right? Like back in the 60s before you had a handheld calculator. I want to look at this one as a tangent line rather than the linearization formula. The linearization formula is just a formula that tells you what the tangent line is. So let's go back to what we were doing in chapter 3 and just write the equation of the tangent line. So I'm not going to draw a picture again. You guys know what the square root function looks like. You know what tangent lines look like, right? So what do I want to do here? I'm going to use the same function. F of x is the square root of x. And then we know that the derivative of f of x is going to be 1 over 2 square root of x. So what am I going to do here to write the tangent line? And let me ask this first. At what point do I want to write the tangent line?
4.
Yeah, why 4?
It's close to 5.
It's close to 5, exactly. So we're going to write the equation of the tangent line at 4. So we know that the point 4, 2 is on the line. So what's the equation going to look like? What do I need to know? I need 2 things. I need a point, which I have, and the slope. How do I find the slope?
Put 4 in for x.
Plug 4 in for x where?
In the derivative.
Into the derivative, exactly. So the slope at 4 is going to be the derivative at 4, which is going to be 1/4. Good. Okay, so then the tangent line, equation of the tangent line is going to be
Y minus 2 equals 1/4 x minus 4.
Now, you guys probably notice here that if I just added 2 to both sides of this equation, then it's the linearization formula. If it was y equals 2 plus 1/4 times x minus 1, that's the linearization formula for the square root function at 4. What?
X minus 4.
I don't know why it's 1, because that's what I wrote. X minus 4, sorry. Okay, so then how do we figure out what the value of the tangent line is going to be at 5? Plug 5 in for x, right? So we're going to have y minus 2. Let's go ahead and add 2 to both sides. So it's going to be 2 plus 1/4 times 1, which is 2 plus 1/4 is 2.25, which tells us then that the square root of 5 is approximately equal to 2.25. Now, I don't want you guys to get the idea that the square root of anything is going to be approximately equal to something 0.25. It just happened that way in both examples. How accurate is that?
Less than before. It's
Not as accurate, right? Okay, so how accurate is it? What
value
is
2.2361.
2.2361 and so on? Okay, you're right, it's not as accurate. Now, I think that's interesting because 5 is closer to 4 than 150 was to 144, right? So why and let me put the graph up here, and I'm going to just go back to our last slide here. Why is it that that we get a more accurate answer in this region here? Sorry. Why do we get a more accurate answer in this region here than we get in this region here?
Because the slope of the line isn't as
No.
Second derivative is closer to 0.
Yes. Good. The second derivative is closer to 0 here, right? Why does that matter?
Because that's the change of slope for the tangent line.
Okay, good. So the second derivative tells us how fast the slope is changing, right? So here, the second derivative is bigger. It's actually going to be negative because it's concave down, right? So the second derivative is negative, but it's curving more. And we measure curvature by taking the second derivative. So it's curving more here. So even though we were closer to the point here, since it's curving more, this part of the curve is less like a line than this part. So the closer the second derivative is to 0, the more like a line the curve is. Does that make sense? So when the second derivative is close to 0, then we're going to get an accurate approximation. If the second derivative is not close to 0, then we have to get really close to the point to get an accurate approximation. Does that make sense? So what we're going to do when we start measuring the error is we're going to use the value of the second derivative to figure out how much error we might have. Did you know that already?
No.
Cool. That's good. I liked it. Okay. Here's another example where prior to calculators, it would be really difficult to do a problem like this. With a calculator, it's really easy to just type in the cosine of 3, and it's going to give you a decimal accurate to 8 or 9 decimal places. Let's see how accurate we can get without a calculator, and then we'll check how accurate our answer actually is. First thing I want to say here is that we're going to approximate the value of cosine of 3 in radians and not in degrees. So if we were in degrees, we'd actually be really close to 0 at the beginning of the period. Since we're doing it in radians, we're pretty close to what? Pi. So we're going to approximate it using pi as our anchor point here. And we'll see how accurate we are here with it. So we're going to approximate close to pi. And I want to use the formula again here, because if you know the formula, all you have to do is just plug in the stuff that you know. The linearization at x is going to equal, well, we're going to say a equals pi, right? We're going to be close to pi here. So it's going to be close to the value of the function. What function are we going to be looking at? What does f of x equal? Okay, so we're looking at the value of cosine of x close to pi. What does the linearization formula say? What's the first thing? F of a. We said a is pi, so what's the cosine of pi?
-1.
Right?
Yeah.
I forgot.
Yes?
How do we know what A is?
We just picked a value that we picked an a value that we know the cosine of, as close to 3 as we could. So the only value close to 3 that I know the value of cosine is at pi. We could maybe try to check like, and we'd have to kind of do a little bit of math here, but maybe 3 pi over 4 would be close to it also. That might give us something more accurate, and we could do a little bit of math with the identities that we know with trig to figure out what 3 pi over 4 is. Actually, we wouldn't really need to do that. It would just be a 45, 45, 90 triangle. That would maybe be a little more accurate depending on how close it is to pi. Okay, so we're going to try pi because it's fairly close to 3. So we're going to start at -1, and then we're going to add on the derivative at a. What's the derivative of cosine? Negative sine. So the derivative is going to be negative sine of x. And what is the sine at pi? 0. times x minus pi. Right? You guys agree with that? Well, this is an easy one to figure out. What's 0 times anything?
0.
0. So what this is saying is the tangent line, and I'm going to write this here, no matter what x is, the tangent line is going to have a value of -1. So in the region close to pi, cosine is going to have values close to -1. So let's see how accurate we are. If we plug in 3 here, so the linearization at 3 is going to be -1, which means that cosine of 3 is approximately equal to -1. Let's see how close we are. Use your calculator to check. Be sure you're in radian mode. If you get an answer close to 1, that means you're in degree mode. Did you get... .9898, you said? Okay. How close are we? I mean, we're about 1/10 away, right? So that's pretty close. Depending on what we're doing with it, that's probably close enough. So as long as we're pretty close to pi, that's going to be pretty close. If we wanted to find the cosine of 3.1, that would be even closer to -1, right? Now we would use the same approximation here, and since the tangent line doesn't have any slope, all of our approximations around pi are just going to be -1. Okay. Again, as Devin suggested, we could use a second derivative to figure out about how close of an answer that's going to be also, and we'll get to that later. This is fun, isn't it?
Oh yeah.
All right, this is the last thing we're going to do, and then I'll give you a little time to work. We'll do this and then a couple examples that use this. Let's say our function is the binomial 1 plus x raised to the k power, and k is some real number. It's just going to be a constant. And I want to figure out about what the value of this function is close to, well, anywhere, but we'll say close to 0 here to start. What do we do? So if this is our function and we are close to 0, what is our a going to be when we do the linearization? 0. So if we want to know what's happening to this close to 0, we'll say a equals 0. So I need to know what a is. I need to know what the function is, and the function is just 1 plus x to the k. What else do I need to know? There's one other thing. I need to know what the derivative is. So what is the derivative here? Let me write this. This is f of x. So what is the derivative going to be? And keep in mind that k is a constant. It's a number. Cool. I agree. Now what? If I want to know what the value of this is close to 0, I want to find the linearization of this close to 0. So I'm going to write this equation here. The first thing is f of a. What is f of a? Let's write it out. It's going to be 1 plus a is 0 to the k. So it's 1 to the k. It's 1 to some number, which is going to be, Joe, it's going to be 1. Okay, plus the derivative at 0. Well, the derivative at 0 is going to be k times 1 plus 0 to the k minus 1. Oop, I don't need that. And what is this part right here going to be? 1. Okay. Times x minus a, and a is 0, so x minus 0. So the linearization of this binomial is going to be 1 plus k times x. So linearization is equal to that, which means that this binomial then is going to be approximately equal to 1 plus kx for values close to 0. Now it's important that we understand that that's if x is close to 0. If x was like 100, this depends on what k is too, because k is going to kind of determine what the second derivative is. Not just kind of, but it is going to determine what the second derivative is. But for values close to 0, this binomial here is going to be really close to 1 plus k times x. Okay, so 1 plus whatever that exponent is times the small x value. So let's say I want to approximate this square root close to 0, right here. What would I do? Using that same idea, that same linearization we just got. And let me write that down here. So we've got 1 plus x to the k is approximately equal to 1 plus k times x. Well, does this look like this? Not really, but kind of, right? What's different about it? Is it raised to a power? It's raised to the 1/2, okay? So in this example, k is going to equal 1/2, right? Let me rewrite it here. It's going to be something to the 1/2, and it's 1 plus, well, 5x to the 4th. So instead of 5x, we have 5x to the 4th. So how would I write that then? How would I write the linearization of that? What do I put in here? Alyssa?
Wait, do we need to find the derivative?
Nope.
No?
We already did the work for it in the previous slide. Abdallah?
Would it be like 1 plus 1/2 times 5x to the 4th?
Yep. So when x is small, the value of the square root of 1 plus 5x to the 4th is going to be really close to 1 plus half of 5x to the 4th. So notice here that this approximation doesn't have anything to do with the square root. We can approximate the value of this square root here without needing to take a square root. And actually this is going to be really accurate when x is small. And when I say x is small, maybe like 0.1. We wouldn't want to get a whole lot bigger than 0.1. But that kind of depends on the second derivative. It depends on how much this function is actually curving, and that's going to depend on what k is. Same thing on this one. For values close to 0, when x is close to 0, we want to approximate 1 over 1 minus x. How can I take this and write it in this form? 1 minus x to the negative 1. So that means that k is negative 1, and instead of x here, what am I going to put? Negative x. Good. So the linearization, the approximate value of 1 over 1 minus x is going to be 1 plus, we said k is negative 1, we said x is negative x, and so it's just going to be 1 plus x. I want you to check this out. I want you to plug into your calculator 1 over 1 minus, well, we want to figure out what, let's say 1 over 0.9 is. The calculator says what? 1.1 repeating, right? So 1.11111, so on. All right. What does our approximation say? 1.1. Because on the bottom here, 0.9 is, we would say x is 0.1, right? If we want to get 0.9, we would take 1 minus 0.1. So x is 0.1 in this case. So we say 1 plus 0.1 is 1.1. That's pretty close, isn't it? And like I said, it would be even more accurate if we use a smaller value. If we put in 0.05, let's say we want to know what 1 over 0.95 is, that would be really close to 1.05. Right? Okay, cool. You were checking me, right?
Yep.
Okay. So the smaller x is, the more accurate this is going to be. And this is just a special case of linearization, where if we have a binomial 1 plus something raised to any power, we can approximate it fairly easily and get rid of the power, get rid of the exponent. And exponents, especially before we had calculators, which again, you guys have calculators now, but before we had them, exponents were not easy to work with. So being able to get rid of the exponents was really useful. Well, that's enough of that for now.